Welcome to Easy Elimu, Learning Simplified, and welcome to this lesson. In the previous lesson, we discussed how to use a YouTube manometer to measure the pressure of gases and liquids. Now in this lesson, we are going to discuss how to use an instrument called Mercury Barometer to measure the pressure of gases and even the variation in air pressure. And thereafter, we will look at how we can use the same instrument to determine the height of mountains and even measure the height above the sea level. My name is Albert. I hope you will enjoy the lesson. By the end of this lesson, I expect you to be able to describe what a mercury barometer is, then construct and use a mercury barometer, and then finally use a mercury barometer to determine the height of a mountain. Now, what is a mercury barometer? A mercury barometer is an instrument which is used to measure atmospheric pressure. It's used to measure atmospheric pressure, and this instrument was discovered long time ago in 1643 by an Italian physicist and mathematician called Evangelista Torricelli. Evangelista Torricelli. Let me get the correct spelling. Torricelli, who was interested in investigating the existence of atmospheric pressure and even the variation of air pressure. Now, during that time, this instrument played a very important role, especially in meteorology and understanding different weather patterns. Remember, this instrument, you also discuss it in geography. It's found in weather stations where it's used to determine atmospheric pressure. And we are going to realize that it's the one that our physicists use, all geographers use to determine the height of different mountains. Now, this instrument employs the fact that atmospheric pressure supports a column of a liquid in a tube. It employs the fact that whenever you have a container containing some liquid, if you bring a tube which is empty, it means it does not have even air inside, the atmospheric pressure outside there will be higher than the empty space inside. Due to pressure difference, the liquid will rise up to some height. So that is the idea that this instrument employs. So if you have a liquid here, then you have an almost, let me call it empty tube. Then there will be pressure difference where inside there is low pressure, outside there is high atmospheric pressure. Now the outside atmospheric pressure will push the liquid to rise to some height. So that is the idea that this instrument uses. Now the construction of a mercury barometer involves using a very thick walled glass tube of about 1 meter. So you have to have a glass tube which is about 1 meter. This should be 1 meter, which is the same as 100 centimeters. Let me use both units, 100 centimeters. So you will have a tube like this one. And then the tube is then filled carefully with mercury. So inside here, you will fill this tube with mercury. You will come with mercury and fill mercury. So you will fill this tube carefully with mercury. Let's say now the mercury, you fill it. After filling it, it will look like this. Now you have your tube here full of mercury to the brim. There's no space which should be left. So after filling it with mercury, this mercury, you make sure that there's no bubble, there's no air bubble which is left inside here. And to make sure that there's no air bubble, you close the end, you close this end here of the tube, and then you tilt the tube several times. You tilt it several times to make sure that any air bubble which is inside has been removed, and then you fill it until it is full. And then now what you do, you take this tube which is full, you invert it, you take the tube which is full, and then you invert it in a container full of mercury too. So you have mercury here. This is a container with mercury. So you will take this tube, this one, and invert it here in upside down, so that the space which is open is in contact with this mercury. So you invert it carefully so that the air does not enter inside. Then after that, so what we will realize is that the level of mercury which was full in this tube will drop slightly. The level of mercury will drop slightly because this tube was 1 meter. So it will drop up to 76 centimeters if you are at sea level. If you are at sea level, this liquid will drop from 100 centimeters to 76 centimeters. So at 76 centimeters, it will stop dropping. What does that mean? It means at the point where it stops dropping, pressure outside is equals to pressure inside. Is equals to pressure inside. Now, what pressure is from outside this tube? We have atmospheric pressure. So here we have pressure due to the atmosphere, which is outside, will be the same as pressure inside. What is pressure inside? It's pressure due to the height of mercury. So at this point where the liquid stops flowing back, the pressure due to the atmosphere outside is the same as pressure of the height of this mercury, which is not flowing back. So the height at which this liquid will stop flowing back depends on the density of the liquid that we are using. And now if we perform this experiment at sea level, which I've said it will settle at 76, the height will be at 76. And if we move to higher altitude, the height will be decreasing, because we said as you move away from the Earth's surface, the atmospheric pressure decreases due to decrease in density of the air column. Now, what if we use water in this case? If we use water, it means if we are at the sea level, the pressure, which will be all the atmospheric pressure at the sea level, will be the same as 76 of mercury. So if we calculate the pressure of mercury, which is pressure of mercury, this pressure of mercury will be the same as the atmospheric pressure at sea level. So if here we have 76 centimeters, it means in meters it is 0.76 meters times density of mercury is 13,600 kg per cubic meter times 10 newtons per kg. In this case, it will give us 360 newtons per square meter. So this is the pressure due to this height of mercury, and we have said pressure due to the height of mercury is the same as the atmospheric pressure. So at this place, atmospheric pressure is the same as the pressure due to the mercury. So if we know pressure due to the mercury, then if we know height of the mercury, then times density of mercury times gravitational constant, this pressure will be the same as when we use height of water times density of water times gravitational constant. So now this height of mercury times density of mercury times gravitational constant is the same as the atmospheric pressure at sea level, which is the same as 103,600 or 360, not 600, 360. Then now this pressure is the atmospheric pressure. So if we want to know the height at which atmospheric pressure will support the water, we will be equals to height of water, which we don't know which height it will support, times density of water is 1000, times gravitational field strength is 10. Then now if we want to know the height which this atmospheric pressure will support the water column, then what we will do, we will simply divide by 10,000. 1,000 times 10 is 10,000, divided by 10,000. Then here it will cancel out like that, and then this 0 will go with this one. We will have 3 zeros here. They will move this one back by 3 decimal places, and then we will remain with height of water, which atmospheric pressure at sea level will support, is going to be 10.3 36 meter. So you see, if we use water of low density, the water in the tube will rise up to 10 meter. But remember, we cannot achieve a tube which is of 10 meters. So in this case, we don't use water, we use liquids which have high density. Now the space which is left up here, remember this tube was full. Now it dropped. So it means this space which is here is empty. It does not have anything because there was no air bubble inside. That space we call it a Torricellian vacuum. Vacuum means a space which is empty, does not have even air, and it was named before the person who discovered or it was named after the person who discovered it, called Evangelista Torricelli. So it's called Torricellian vacuum. So after constructing our mercury barometer, we have said the space up here is empty because the mercury was full and there was no air bubble. So it means this is a vacuum, which we have called Torricellian vacuum. Now we have to test if this space is indeed a vacuum. Remember, at sea level, the mercury or the atmospheric pressure will support a height of up to 76 centimeters. So what you do to test if this space is a pure vacuum, you tilt your barometer until the far end of the tube is below 76. If the mercury rise, because at this place mercury will or the atmospheric pressure will support a height of up to 76. If it's below 76, the mercury should fill the tube because it's below the height which the atmospheric pressure can support. But so in this case, if it is fills, you will say the mercury is okay or the barometer is okay and the space is a pure vacuum. But if you tilt and then there is some space left, it means you left some air bubbles inside this tube, and this air is exerting some pressure because we said whenever we have air, we have what we call air pressure. So here this barometer is faulty, so you have to remove that tube from inside the mercury, you fill it properly, you tilt, and then you insert it carefully. So if you want to test, you tilt below 76. If the mercury fills the tube, the mercury is okay. If it does not fill the tube, it means it has some air bubbles or some air inside, and that air is affecting the height which mercury will support or which the atmospheric pressure will support at that place. Now we can determine the height of the mountain by using the ideas that we have discussed. For example, if you have your mountain like this one here, around this mountain we have air. That is a fact. We have air here. We have air from the top, from the bottom to the top, and this air is exerting what we call air pressure, which is atmospheric pressure. And now, for us to calculate this atmospheric pressure or air pressure, then we will need height of this air from the top to the bottom. So this will mean the height of air times density of air times gravitational constant. In this case, we would have calculated the pressure of the air exerted by this height. Then now, density of air is a constant. It's 1.25 kilograms per cubic meter. Then now, if we know the density of air and we know the height of the mountain and the gravitational constant, we will calculate the pressure between points, let's say A and B. But now we don't know the height of the air, that is the height of the mountain. What do? We will come with our mercury barometer. Our mercury barometer like this, we put it at the base. At the base, after putting our mercury barometer there, remember we have said it will support some height. It will support some height. If it's at sea level, the atmospheric pressure here will make this mercury to rise to 76 centimeters if it's at sea level. And remember we said at the base of the mountain we have high atmospheric pressure. At the base we have high atmospheric pressure. As you move outside the sea level, atmospheric pressure decreases because we said in atmospheric pressure, as you move out, the density of air will decrease. So up there, up here, we have low atmospheric pressure. So if we have low atmospheric pressure, if we bring our mercury barometer like this one and put it there like that, the height which this atmospheric pressure which is low will support will be relatively smaller than the one which is supported at the base. Let's say now it supports 60 centimeters. So at the base, it's supporting 76. At the top, it's supporting 60. So now the difference in pressure height, or the difference in mercury height between the base and the top, is the difference in height is 76 centimeter minus 60 centimeters. So which is 16 centimeters of mercury. So if we know the height of mercury between the base and the height, and we know the density of mercury, we can be able to calculate the pressure difference between the top and the base. And remember, we have said if you want to know the height of this mountain, then you must get the pressure at the top and the pressure at the base, or the difference in pressure between the top and the base. Now, in this case, if we use this density of mercury, so if we want to know pressure here, pressure of mercury is going to be height of mercury times density of mercury times gravitational constant. We will get the pressure difference between the top and the base. And also, if we need the pressure difference between the top and the base, that is A and B, we said we can get it like this. Then we will not be wrong by saying P, we cannot be wrong by saying pressure of mercury is the same as pressure of air between the top and the base. But now, what is pressure of mercury? Pressure of mercury is here, which we can write as height of mercury times density of mercury times gravitational constant is equals to pressure of air. Pressure of air is found by height of air times density of air times gravitational constant. Now, for us to get the height of the mountain, if we know the height of mercury, or the height of difference of mercury times the density of mercury times the gravitational constant, we will equate it to height of air, which is the same as height of the mountain, times density of air times gravitational constant. Now, in this case, let's say the difference is 16 here. Then in this case, if the height difference is 16, we will use 16 over 100. Then we convert it to meters, times density of mercury, which is 13,600, times gravitational constant, which is 10. It will be the same as height of air, or which is the height of the mountain, times density of air, we said is 1.25 times 10. Now, for us to get the height of the mountain, the first pressure here of mercury is 21,760 is equals to height of air times 12.5, that is 1.25 times 10, which is 12.5. So if we need the height of the mountain, we will divide by 12.5 divided by 12.5. Now here it will give us the height of air, which is the same as height of the mountain, is the same as 1,740.8 meters. So the height of the mountain, or the height of air from here to this point, is 1,740.8 meters. So what you do, you take the barometer at the base, you take it at the top, then you get the height difference. And then there you will use the density of air times gravitational constant times the height of air, which you are looking for. Then you will use this relationship to determine the height of mercury. So we are going to do an example so that you see if you have grasped this concept. Here is a question which we can do to understand better. The question reads, the barometric height at the top, so we have top and base of the mountain. At the top is 65 centimeters of mercury. And then at the base, which is standard atmospheric pressure, is 76 centimeters of mercury. Then we are given density of air is 13,600 kgs per cubic meter. This for mercury. Then we have density of air is equals to 1.25 kilograms per cubic meter. Then they are asking what is the altitude of the mountain. They want us to calculate the height due to this air here. So what you do, we said pressure due to mercury, or pressure difference due to mercury, is the same as pressure of the air between the base and the top. And this one, we can write it as pressure due to the mercury is change in height of the mercury, which is change in height of mercury times density of mercury times gravitational constant is equals to the pressure due to air, height of air, which we don't know, times density of air times gravitational constant. Then now, what you do, you can see gravitational constant disappearing both sides. You can even cancel that for easy because we cannot carry that 10 all through. So now we will remain with change in height of mercury times density of mercury is equals to height of air, which is the same as height of the mountain, times density of air. Then in this case, do we know the height change in height of mercury? Yes, 76 minus 65 over 100 to convert to meters. Then times density of mercury is 13,600 newtons per kg is equals to height of air, which we don't know, times density of air, which is 1.25 kilograms per cubic meter. Now, for us to remain with height of air, which is the same as height of mercury, we will divide by 1.25. You divide by 1.25, which is going to be, this one is going to cancel out with this one. And then height of air, which is the same as height of the mountain, is going to be 0.1, because 76 minus 65 is 10, divided by 100 is 0.1 meter, times 13,600, then you divide by 1.25. 13,600, remember, is in kgs per cubic meter, and this one is also in kgs per cubic meter. So kgs per cubic meter will cancel in both sides, and our answer will remain in meters. Then now in this case, a height of, let me use this ink, height of air is going to be 0.1 times that, 13,600 divided by that, which is going to be 1360 divided by 1.25, which is the same as 1088 meters. So in that case, you would have calculated the height of the mountain, which is the height of air. So what you do, you get the height difference between the base and the top. You use it here. You make it. You use it as in SI units. Then times the density of mercury. Gravitational constant is gravitational constant, will cancel out, and then you equate it with the height of air times the density of air. Then you solve it like that. Then you solve and get the answer. Now, this is another question, and since it is similar to what we have just done, it's better I leave it as an assignment for my students. Try it. If you get any difficulties, feel free to visit ECLM Learning Simplified website or app, and you will get all questions, including this one, with solutions, and you will enjoy learning. So that marks the end of our lesson today. See you in the next lesson.